Thank you. And welcome to Moving Java Forward Faster. So, what's going on in Java? Well, we shipped Java 9. That's a good thing. Java 9 is here. We shipped it just over 4 months ago in September. That means that Jigsaw is here, and that means that the modular platform is here, and it means that almost 100 other new features, large and small, are here. So you might be wondering, after all this work, what's next? Well, hopefully one thing that's next is adoption by the entire Java ecosystem. How many people here have tried out Java 9? OK, good. How many are using it in production? A much smaller number. That's typically what I see when I ask these poll questions. Now, I understand there may be some trepidation about moving on to 9. You may have heard in particular that Java 9 breaks everything. That's not true. What is true is that it breaks some things. Java's core value, after all, is compatibility, and we took this very seriously as we sort of forklifted the platform up and re-engineered a module system underneath it. That's one reason, frankly, why it took so long. I'm not going to go into all of the details here. Many things do just work, or they work with modest changes. You don't have to take my word for it. Just after Java 9 was released, I asked the following question on Twitter. Do you maintain a popular Java library, framework, or tool? If it works fine on JDK 9, then please reply with its name and version. I got quite a lot of replies, and some are still straggling in these days. Here's a summary. It's not exhaustive, does not include all of the replies. All of these tools and components and more work fine on Java 9. In many cases, they worked without change. In some cases, their maintainers had to make a modest number of fixes. So this list includes the major IDEs, Eclipse and IntelliJ, major build tools, Ant, Maven, and Gradle, test frameworks, JUnit, TestNG, popular libraries, ByteBuddy, Jackson, Log4j, Hibernate, Juke, Jetty, and a whole bunch more. The entire Spring framework works fine on Java 9. So my key advice to you, if you're exploring 9, if you're starting to play with it to see if an existing system works, is first be sure to upgrade to the latest versions of all of your tools and dependencies. OK, so it's time to adopt Java 9, but after that, really, what is next? To understand more about the future, I'd like to take a brief look at the past. For 20 years now, Java has evolved in large, irregular, and somewhat unpredictable steps. Each release has been planned around one or a few really big features, and the schedule has been adjusted, sometimes more than once, as needed to accommodate those big features. Now that's good, or at least OK, for those big features, but it means that smaller features have to wait. A small feature could be done 2 years before the GA release, and everybody has to wait for it before they can use it. That's no fun. So we've wound up with releases that are grand and majestic, but rather slow-moving. For Java to remain competitive in this day and age, it must not just continue to move forward. It must move forward faster. And that's why we're switching to a new release model with a new feature release every 6 months on a strict time-based schedule. Every 6 months, there will be a new Java feature release. Let's try to visualize this. Here's a timeline. So we just shipped Java 9, up there, September 2017. With a new feature release every 6 months, the next release will be in March of 2018. My goodness, that's in just 6 weeks from tomorrow. A feature release can contain any kind of feature. It could even contain a feature removal. The key point here is that features will go in only when they're nearly finished, so that we can maintain this train of shipping every 6 months, whatever it is that we have ready. It's OK if a feature misses the current release, because the next one is just 6 months out. Now, the proposal in the OpenJDK community is that OpenJDK contributors will support each of these feature releases for at least 6 months until the next feature release, and quite possibly longer. We'll do the usual style of quarterly update releases every 3 months. This is okay for bleeding edge developers who are deploying their own runtime along with their application in a Docker image in the cloud or whatever. It's not so good for more traditional enterprises who would like longer term support and less churn in their production systems. So every 3 years, we'll do a long-term support release. The first one will be the release in September of 29, and the next one will be the one in September of 2021. So if this diagram were a little bigger, you could see up top that 8 was effectively the last long-term support release. 9 is not a long-term support release. So 9 is called 9. There remains the question of what to call all of these following ones. And as you might know, my initial suggestion was that we adopt a time-based scheme, vaguely in the style of Ubuntu, with which you may be familiar. There was a fair amount of feedback on this. A lot of it was very emotional. Some of it was quite rational and pointed out various deficiencies in this scheme. So we're not going to do that. We will do the simpler and more logical thing of just calling them 10, 11, 12, 13, 14, and so forth. So switching to a new release model, six-month cadence, those of us who work at Oracle are also making changes in what we do. One change is, for the first time, we're going to ship GPL licensed builds based only on OpenJDK source code. So if you don't like the Oracle binary code license, if GPL is a better license for your environment, then you can get these builds, also from Oracle, tested in the same way as the Oracle commercial builds are. And you can get them today for both 9 and the 10 early access releases at jdk.java.net. We are going to open source all of Oracle's commercial features. The extra features that you find in an Oracle JDK build, we will either remove them because nobody cares about them, or in more significant cases, we will open source the code and propose to merge that into the OpenJDK code base. The main features of interest here are application class data sharing, also known as AppCDS, Java Flight Recorder, Java Mission Control, and the Z garbage collector. AppCDS is already in JDK 10. We open sourced the Z garbage collector last fall, and we're still working on JFR and JMC. Another change is that Oracle will focus primarily on Linux, macOS, and Windows on x64. Oracle won't be shipping ARM32 builds or 32-bit x86 builds anymore. You can do them yourself. You can get them from other people. So Oracle is going to stop doing that. And finally, Oracle will sponsor a few engineers to work in the OpenJDK community to try to establish an open build and test system. This is kind of the last bit of infrastructure that the OpenJDK community needs so that anybody can build and test any kind of contribution, and ultimately, in the long term, even maybe get binaries directly from OpenJDK rather than a specific vendor. Now, as with any enormous change, there are lots of worries and some confusion. So I'd like to try to address the top 5 misconceptions about the new release model. So, number 1, non-LTS releases are experimental. They're just fancy betas. You can kind of ignore them. It's okay. No, the only difference between a non-LTS release and an LTS release is that the LTS releases have a longer support timeline. We will, in general, not try to plan a feature for, oh, this has to be in the next LTS, otherwise it's going to have to wait 3 years. That's falling exactly into the trap of the big feature releases that we so carefully recently crawled out of. Number 2, every feature release will be as disruptive as past feature releases. No, that's not true either. The rate of innovation, and remember, innovation correlates with the disruption, the rate of innovation won't change over time. What changes is the rate of opportunities to deliver innovation. Innovation delivery increases. Number 3, to remove an old feature requires 3 years advance notice because that's the delta between long-term support releases. No, to remove a deprecated feature requires a production-ready build that issues a suitable warning, because after all, a build that issues a warning that annoys you is probably going to get your attention better than an obscure release note that you never read. Does that mean that we will introduce a feature in one release and deprecate it 6 months later, or deprecate a feature that's been around for 20 years with only 6 months notice? No, of course not. There's room for judgment here. If something is really popular and it's been used by a lot of people, it will take a year or maybe even longer to be between deprecation and removal. Number 4, if you maintain an infrequently migrated system, such as an app server on a big piece of hardware, then you can ignore the non-LTS releases. That would actually be unwise. What you should do, even though you're not going to deploy the non-LTS releases in production, is test with those when they come out. And that way, by the time the next LTS does roll around, you'll be prepared. You will have much less change to deal with in terms of upgrading your own system to run on that new LTS release. Finally, number 5, there will never be more than 2 updates for any non-LTS release, and there will never be more than 3 years of support for any LTS release. No, that's not true. It all depends on who shows up. These times are meant to be minima, not maxima. They could well go on a lot longer. It depends on who shows up in the OpenJDK community to help maintain these things. It also depends on commercial vendors who may offer their own options for support, usually something that you have to pay for. All right, speaking of showing up, there's been some confusion in the ecosystem around what Oracle intends to do in the OpenJDK community going forward, so let me try to clarify this. Oracle intends to pay engineers to lead and contribute to every JDK feature release, as Oracle and Sun before has done for many years. Oracle will lead and contribute to at least the first 2 quarterly updates of every JDK feature release. Oracle will publish OpenJDK builds for at least the above releases, possibly more. Oracle will lead and contribute to the JDK 8 updates project until at least January 2019. And finally, if and when Oracle, the business side of Oracle decides that it's not worth funding engineers to work on specific releases anymore, we will ensure a smooth leadership transition, as we have tried to in the past, so that other OpenJDK contributors can step up and take on the maintenance of these releases. So the phrase "at least" occurs on this slide many times. Remember what I said about minima. Just as Oracle historically has done with public updates, these timelines may be extended. What we're committing to here is the very least that Oracle will do. They might turn out to be longer. We'll have to see it. It all depends on the situation at the time. Okay, so we've got this train model. A feature release is going to go out every 6 months, like clockwork. Time, like the tide, moves on. It waits for no one. In order to keep this going, we need to maintain a pipeline of features in progress. And that's especially important since features can only go in when they're done. You can't check in a half-baked feature to one of these releases because in a 6-month cycle, it'll be very difficult to pull it out. So our primary backlog of feature ideas is in the JDK Enhancement Proposals that we maintain at this URL in the OpenJDK community. We've been using JDK Enhancement Proposals, also known as JEPs, since 2011. We used them for Java 7, for Java 8. We use them for 9. We're now using them for 10 going forward. There are quite a lot of them by now. We're up to, I think, 300 some, with switch expressions being the last one that's actually a candidate to go in. Of course, many of the ones that scrolled by there are actually in 7 or 8 or 9. And then one of the more interesting parts of this page is the unsubmitted draft JEPs at the bottom, where you can see things that people are working on. They haven't submitted them for any kind of review yet, but sometimes they contain kind of interesting ideas, such as, for example, raw string literals. At the very bottom, something that some people have desperately wanted for many years. So we shipped 9. We're moving towards 10. As we look at the release, the question is not what features are planned for 10. You know, I've had VPs at the company ask me, "Oh, so what's planned for 10?" And the answer is, I don't know. You know, whatever's done is what goes in. So the question is really what features are ready for 10. Here are the features in 10. There are only 12 of them. Well, we only had 6 months. That shouldn't be a huge surprise. Let me go through these briefly. Local variable type inference. The var keyword is now something that you can use in Java. I'll show a little example of this in a moment. We've consolidated the JDK forest into a single Mercurial repository. This is of interest primarily to those of us who work on the JDK itself. It used to be that the JDK source code was in essentially a tree of Mercurial repos. There were 8 or 9 of them. Fairly clumsy to work with and impossible to do an atomic transaction on the tree that crosses component boundaries. So if you're working on a change in an API that also requires a change in hotspot, you had to commit to 2 things and hope that nobody got an inconsistent view. So that's mainly an engineering thing. We have a garbage collector interface to make it easier to experiment with new garbage collectors in the hotspot JVM. Parallel full GC for G1, one of the last big things that G1 has been missing. Application class data sharing, I mentioned that earlier. This is a feature that allows you to run the VM and have it pre-digest a set of classes that you specify, write the result into a file, which you can then memory map in later on when it starts up to improve startup time. Thread local handshakes, a way to make threads work more efficiently in the VM. We've removed the native header generation tool, Java H, which has been around since the beginning of Java. The reason for doing that is that Java SE can do this too, and it does a better job of it. Additional Unicode language tag extensions, because Unicode always adds stuff, and that's what happens. Heap allocation on alternative memory devices. If you want to, you can cause the heap to be allocated on an NVMe chip and experiment with persistent memory. It's more of an experimental feature than something I would suggest you actually use. An experimental Java-based JIT compiler. So this is related to one of our long-term projects, Project Metropolis, where we're looking at the possibility of replacing the hotspot VM's high-performance JIT, known as C2, which is written in C++ and is a code base that's almost 20 years old and is getting to be very difficult to maintain. We're looking at replacing that with a compiler written in Java itself, a compiler named Graal out of Oracle Labs. It's a very interesting project to think about. Well, okay, the runtime compiler is written in Java itself, so at some point it has to compile itself, and you get into all these fascinating self-application scenarios. But it's quite cool and shows good promise. We have root certificates in OpenJDK now. It used to be that if you did an OpenJDK build, you would have no root certificates. So if you needed to open an SSL connection, you would find that difficult. You would have to go get some from somewhere if you wanted to be able to trust anything. So those are in OpenJDK now. Time-based release versioning. This was a small tweak to the release version, the new release versioning that we introduced in 9, in order to fit it into the 6-month release model. So those are the 12 things in 10. There are a bunch of little bug fixes and enhancements too, of course. Let me show you a little bit about local variable type inference, which is pretty cool. So it's a popular saying that, oh, Java doesn't have type inference. It's statically typed. You have to type out everything. It's really verbose, and it's a pain. Actually, Java has had type inference for a very long time. When we introduced generics in Java 5, we introduced a bit of type inference so that if you invoked a generic method, you don't actually have to type that string before the method name. You can omit it. The compiler will deduce it for you. In Java 7, we cottoned on to the fact that, well, gee, you've got string there appearing 2 times. The compiler can unify those and figure out what it ought to be in the actual constructor invocation. So you can just type an empty pair of pointy brackets, and the compiler will do the work for you. When we introduced Lambdas in Java 8, we added additional type inference. You can type the type of a Lambda parameter if you want to, but you don't have to. You can just type s.length equals 0. Now, in 10, we've introduced local variable type inference. The point here is to reduce some of the verbosity in code like this. You've got buffered reader equals new, buffered reader, new file. Like, how many times do I have to write buffered reader? Now, sure, my IDE could maybe write the second one for me, but how many times do I have to read it? So let's just get rid of that. and let you type var reader. So this is the same token that's used in JavaScript. That doesn't mean that Java is going over to dynamic typing. This is still statically typed. It's just that the type is inferred by the compiler. And this turns out to be really pleasant for small snippets of code like this. You know, opening a new URL connection, you're seeing all these types with mixed case letters, and they're kind of, it's just a lot of stuff to parse. So this really seems much nicer. All right, here's the JDK 10 schedule. We are on the verge of shipping the first release candidate. The first release candidate will be built tomorrow, should be available sometime tomorrow or on Friday. So if you haven't tested it, now is the time. Please download it and test it. And if you find a showstopper bug, please report it. If you find a non-showstopper bug, please report that too, and we'll fix it in 11 or 12 or something. But we're really interested in experience reports of real systems running on these builds, because we're trying to be done. All right, so going on from 10 to 11, again, the question is, what features are ready for 11? So here are the JDK 11 features so far. There's still time for a few more to get in. One is JEP 309, dynamic class file constants. If you're familiar with invoke dynamic, which we added in Java 7, dynamic class file constants essentially does for constants in the class file what invoke dynamic did for method invocations with the introduction of method handles. It's a fairly specialized feature, but it will be of use to people implementing languages on top of the JVM, not just Java, but many other kinds of languages. Epsilon, an arbitrarily low overhead garbage collector. So this is a contribution from Alexei Shipilev at Red Hat. Epsilon is a GC that never actually GCs. All it does is allocate. And allocates and allocates and allocates, and if you run out of memory, the VM halts. Why is this useful? It's useful for a few things. One, it's useful for benchmarking, where you want to measure things like the actual allocation code or other aspects of your system, and you want to be guaranteed that the GC will never actually run and cause your code to run slower. It's also useful for extremely short-lived transactions. If you're doing one VM invocation per transaction and you have enough memory, you could just allocate enough memory, use Epsilon, and know that you're never going to have a GC pause. It's crude, but it can be effective. Remove the Java EE and Corba modules. This has been in the works for a long time. We deprecated these for removal in Java 9. They will be gone in Java 11. And finally, local variable syntax for Lambda parameters. This is just a cleanup on the local variable type inference that I showed a moment ago. So that's what's in 11 so far. There will likely be a few more things in 11, but 11 ships in September, so it's not like there are going to be 30 more features in there. From 11 moving on, well, we need to figure out how to feed the pipeline again. Again, the primary source of the backlog are the JEPs. But how do we figure out where does the JEP backlog come from? And the answer to that is the JEP backlog generally comes from big projects that we've been working on in the OpenJDK community, in some cases for quite a long time. So I'd like to mention those briefly. So we have Project Amber, which is looking into ways to right-size language ceremony. Java, as we know, is well known for being more verbose than many people would like. So Amber's trying to address that. Project Loom is seeking to bring continuations and fibers to the Java virtual machine and to the platform. This will enable a much cleaner, simpler model of concurrent programming. Metropolis, this is the Java on Java VM idea that I mentioned a moment ago. The initial goal is to see if we can use Graal as a replacement runtime compiler. A longer-term goal is to write as much of the Java virtual machine in Java as we possibly can. Panama, foreign function interface and data layout. Portola is a port to Alpine Linux using the Muzzle C library, which this combination works really well in Docker images, lets you omit hundreds of megabytes from such images. Shenandoah, an ultra-low pause time garbage collector. Valhalla, which is about value types and specialized generics. And finally, ZGC, which I mentioned earlier, a scalable, low-latency GC. So that's the list of the big projects. And as always, our philosophy around this is we want to evolve Java thoughtfully. We're not going to do features just because they're popular, just because they're in some new fad language. We will always keep compatibility in mind as we seek to improve developer productivity and keep up with hardware and software trends. So right now, I'd like to dig a little bit into Amber, which is ongoing. Amber is actually where local variable type inference came from, but the folks working on Amber are cooking up a bunch of related ideas that I'd like to show you here. The language ceremony, the Java boilerplate, we find it often arises when dealing with simple data. Consider a canonical example. You want to represent a geometric point. So you have to write a POJO, plain old Java object. Okay, sure, we've been doing this for decades. IDEs can generate these for you, but it doesn't actually help with reading, and having readable code is a key to having maintainable code. Once an IDE has generated it, well, a mistaken edit could introduce a bug, turn your hash code into something that has lots of collisions, things of that nature. And a higher level observation here is that the encapsulation that this class gives you for this plain old data is actually not necessary. You just have some data. I've got an X and a Y. Why can't you make me something that will hold an X and a Y and let me pass them around easily and manipulate them? What we need is a way in the language to say this class is just a transparent container for some data. And that's where the idea of records comes from. So a record lets you say in one line what all of that grayed out POJO code was doing. I'm going to declare a record. It's a kind of class. It has a double X element and a double Y element. Its name is point, and the rest just comes for free. Records are a bit like enums, which we introduced back in Java 5. Enums are classes, but it's a shorthand to the compiler. You can type enum and the declaration, and the compiler will generate a bunch of code for you. Records are much the same thing. Now, records have some important properties. These properties basically ensure that they really are just containers for data, that you can see the state, the whole state, and nothing but the state. So one important property is that if you have arguments that you pass to a constructor, a record constructor, if you do that twice, you will get record objects that are dot equals, absolutely guaranteed. And then going in the other direction, records are reconstructable. If you have a record, you can extract its elements, pass those values into another invocation of the constructor, and you will get a record object that is also dot equals. Now, you can customize records just as you can customize enums. You can customize a record. If you don't like the hash code that the compiler provides, you can write your own. You can add additional instance methods. Here's a method to compute the norm of a point. You can even customize the constructors. If you want to check, for example, in this case, you want X and Y never to be at the origin, then you can check that and throw in a legal argument exception. You might think, oh yeah, maybe you could add another field, but actually you can't. And the reason for that is so that we can preserve those properties I showed in the previous slide, that a record really represents the state, the whole state, and nothing but the state. There isn't additional state that can kind of leak in, so that's actually not allowed. Let's turn to a less trivial example. Rather than points, let's talk about expression. So imagine we have an empty interface called expr. We're going to build little arithmetic expressions. So we have a constant record, carries an int value. It implements expr. We have an add record. It has a left side and a right-hand side. It also implements expr. And we have a multiply record. It too has a left side and a right side. So given these declarations, we can build up a little expression. Here's an example, 1 plus 2 times 3 plus 4. You just invoke the constructors, you built a little tree, and bound that to E. Now, suppose we want to evaluate this expression tree. What's the usual way to do that sort of thing in Java? Everybody's digesting their lunch still. OK. The usual, or at least common way to do that in Java is to write visitors. So we introduce a method in the expr interface. We have each record implement that method. And so the code to evaluate a particular expr node is distributed throughout these different record declarations. Now, that might not look so bad here, but with a larger, more complex set of related data structures, it gets quite hairy. If you ever, an example of that you could find easily is the Java C source code, which uses visitors very heavily, and it's quite difficult to get used to reading all of that. It's often clearer, in other words, to handle all of the different cases in the same body of code. Now, we can do that today in one method here with a chain of ifs. If the expr is a constant, then cast it and take the constant value. If it's an add, then cast it and do the addition, and similarly for the multiply. Problem here, of course, is this is a linear chain of if statements. It's going to be slow. What we really want is a switch, which can be much more efficient. So over the years, many people have requested a type switch, be able to switch on the type of the switch argument rather than its value. We could do that, but it's still kind of clunky because you have to cast and bind the value in each arm, and that's fairly tedious. So instead, what we're going to do is generalize the existing switch statement. And here what we have in orange are what we call type test patterns. So that constant C in orange will test whether the expr E is an instance of the constant record type. And if so, it will bind that value to this variable C, whose scope extends only to the body of that case statement. And then the code can return C.value. Similarly for add and for multiply. So this is an improvement, but you still have to think about control flow. What if you forgot one of the returns? Then you'll drop through and return possibly some incorrect value. So let's go one step further more. Let's allow a switch to be used as an expression. So this is an expression switch, or switch expression, either way, same thing. So this expresses more clearly what you mean, since it is essentially a big function. It's a recursive function. And all you need to know is the value you're returning in each case. You don't need to be bothered to reason about, oh, am I returning? Am I going to fall through here? You won't be tempted to implement some hack where you fall through one day and then 3 months later forget why you fell through and take that out and cause the code to be incorrect. Now, this is better. There's still something, we can improve it even more. There's this default case, which is kind of annoying. I mean, we know that an expr is going to be a constant and add or multiply, and that's it. But we have to include this code to keep the compiler happy. Well, what if we could say that a particular type is sealed? That is, that we know every one of its potential subclasses. So if we seal the expr interface, then we know that those record types, constant, add, and multiply, which are all in the same source file, are the only possible implementations of that interface. This allows us to get rid of the default arm. Those of you who are familiar with functional programming may note that we have just added algebraic data types to Java. Very useful tool. All right, what more can we do? Well, quite a bit, it turns out. So far, we have these type test patterns. The type test patterns test whether the value is an instance of the type, and then bind that value. Type test patterns are a generalization of existing patterns, where we can basically retroactively conceive of what we have been writing in case statements for years as degenerate kinds of patterns. So, a case with an integer constant, that's a pattern. It's a degenerate pattern. It tests whether the value is 42. It doesn't bind anything. Case foo, same thing, but for a string. Case constant C, this is the type test pattern we've just introduced. We can generalize patterns a bit more. they can not only test a type, but they can extract something from the type, maybe multiple things from the value, and then bind to one or more variables. So we can, for example, write constant int value. And in the body of that case statement, value will be bound to the int that's inside the constant object rather than the constant object itself. And we can do similar things for add and for multiply. And so now our code becomes even simpler. Now, suppose for the sake of this example that multiplication is an expensive operation on your computer. You want to avoid it. We can do a little bit more. I mean, you could write this code by hand, right? In the multiply case, well, look at the right-hand side. If look at the right-hand side. Is it a constant? If so, then do the obvious optimization to avoid the multiplication operation. Otherwise, do the multiplication operation, and then the corresponding thing for the other side. But this is the same kind of test and cast code we were complaining about before. So let's generalize patterns even further to test not just types, but values. So constant 0 will be a pattern that will match a constant object whose value is 0. And multiply of P and Q will match a multiply object whose contents match the patterns P and Q. So these patterns can now nest. With that, we get a much more compact body of code. Last couple of improvements, we can do type inference. You don't have to type the type all the time. There's another kind of pattern, var x. You can just type var rather than the type. And finally, so you may note that some of these values are never used. Well, if they're never used, why should you have to invent a name to bind them? So let's allow case of underscore. We have rehabilitated the underscore character in Java, so you can use it for a wildcard. You can use it in a pattern. Basically, you're saying, I don't care what this value is. I'm never going to use it. I don't need it. Don't bother me with it. Okay, so that's a look at Amber. The primary features we're exploring there are records, pattern matching, expression switch, and sealed types. These all fit fairly naturally together to enable less error-prone code, more maintainable code, no more visitors, yay, and simplified data-oriented programming. All right, let me skip ahead a bit here. Back to the list of projects. So all of these projects are things that people in the OpenJDK community, not just from Oracle, are investing very heavily in. They're long-term investments. In some cases, these have been going on for quite a long time. A couple of other cases are newer. But this is what will make the train model run. Right? This will be the kind of fountain of features over time. They will eventually show up in releases as we go, along with many smaller enhancements and features along the way. All of this work will help Java move forward faster. Don't believe a word I've said? Thank you very much. I think we have time for a few questions.
10 minutes almost.
10 minutes? Okay. He's got the mic. Raise your hand if you have a question. Simon.
Oh, here.
I think this is a good question. So last night when we were in the RC Architects talk, I asked about the idea of a tuple. But isn't a record essentially like a tuple? I mean, doesn't it suffer from the same problems that Stuart was talking about in terms of the problems of type erasure when you're using generics?
Isn't a record like a tuple? No, a record is not like a tuple, because a tuple will be an element where you know the type of each thing, but you don't know the name of each thing.
Okay.
And it's not uncommon to see languages introduce tuples and then realize, oh, well, yeah, wouldn't it be nice if they had names? Python has a notion of named tuples, which are basically records. But they got there by having tuples first for many years and then realized, oh, yeah, well, maybe we'll put names in there too. And so they have named tuples. But without names, it's difficult to fit a new linguistic concept into the Java programming language, because as I said yesterday, Java is primarily about nominative types. Types get named, and components get named. Java is not a language where you find unstructured data of, oh, just S expressions or tuples or lists of arbitrary stuff. Other languages do that, and there are some beautiful languages designed around that paradigm, but Java is not one of them.
Oh, wait. Huh. Oh, passed it in?
When would you use a record and when would you use a value type?
When would you use a record? When would you use a value type? That's an excellent question. And if I had more time, I would go through my Valhalla slides. You can use a record as a value type. So if you've got points and you want to encode them efficiently into an array, you can prepend the idea is, there's no code that actually does this yet, you can prepend the value keyword in front of your record declaration, and that will make it a value type. They're orthogonal concepts. Well, if there are no other questions, I could back up to those slides. What the heck? Yes?
Seems to me that Project Metropolis would benefit greatly from Project Amber.
Project Metropolis would benefit greatly from Project Amber. Indeed, it would. Project Metropolis. So all of these projects are fairly deeply intertwined. For Metropolis is probably the longest term of these. For Metropolis to succeed, we don't need Amber, but it would be really nice. We absolutely do need Valhalla. There's no way we will write a Java virtual machine in Java unless we can have value types and get past the current bloated sorts of memory consumption that you find with Java. So Metropolis depends very strongly on Valhalla. Would it benefit from Amber? Sure, but theoretically at least we could do Metropolis without that. Any other questions? 5 minutes? Okay, well, I can show the Valhalla slides. No takers? Okay. All right. Okay, what's Valhalla all about? Value types and specialized generics. Hardware marches on. Like time, it waits for no one. Hardware is getting more and more complicated. It's not getting particularly faster. And we're getting all these caches between the processor cores and the memory system. Caches which occasionally leak information, but I'm not going to talk about that here. So cache performance is a huge aspect of program performance these days. Suppose you have a point, as we had before. How is that represented in memory today? If you want an array of such points, well, you make an array. It's got a header. It's got a bunch of elements, and each one of those elements, what's in those? Well, you have a pointer off to another object that has a header and carries an x value and a y value. Now imagine you're doing some kind of big data number crunching, and you've got an array that covers a gigabyte. This is an awful lot of unnecessary data. It's an awful lot of unnecessary pointer chasing. You're basically beating up on your cache subsystem really, really hard, unless you got very lucky with the data layout, which usually you don't. So this is where value types come in. Record point of double x and double y, write value in front of it. The essential difference between a normal object and a value object, a normal type and a value type, is a value object is not necessarily an object. It's a collection of values. If you get your hands on one of these values, you cannot test it for double equals equality, or if you do, it might give you a surprising result. You can't synchronize it because it doesn't have a monitor, because it might not actually exist on the heap in memory. So they're fairly limited, but by giving up some of those things, you can achieve some pretty big performance benefits. So here's our previous data layout. If we have value types and use a value record for these points, everything just gets flattened into one array. No added indirection. You wind up with an array that looks just like what you would have in C or Fortran, and you can march along this, feeding your cache subsystem in a very sane way, which will probably be able to predict for you, and you'll get way better performance. As my colleague John Rose likes to say, value types, they code like a class, they work like an int. To make this work, we have to do some other changes, and that is to heal the rift in the generic type system between primitive types and reference types. Right now, if you have an array list of integers, then you'll have that really ugly, inefficient memory representation that I showed. We also need to enable you to write array list of int and have the representation of that be as efficient as the simple array of points that I showed on the previous slide. So that's Valhalla in a nutshell. Main benefits: improved memory density, higher performance, better cache performance. All right, how are we doing on time?
A couple more minutes.
A couple more minutes. Any more questions?
About records, I guess once that is in place, there's no need to use beans anymore.
So with records, once that is in place, there's no need to use fields? Beans. Oh, Java beans. Well, if you have legacy code, you will probably be using beans for many, many years to come. Yes, there's definitely overlap there. A record is, in a way, you could see it as a sedimentation of the bean concept into the language, but in a way that fits well with the language rather than the sort of naive macro expansion sort of thing that people have been suggesting for many years. So yeah. Yes, sir.
Will Valhalla introduce a value type string? I mean, I know that string can't be moved to be a value type, but
Will Valhalla introduce a value type to replace string or augment string? That's a fascinating question. It might. Okay, and this may be one of those changes that we make that, yes, strictly speaking, is incompatible, but we make it over several releases and help people prepare for it because the win could be huge, absolutely huge. Another cool thing you can do with value types is the VM has the opportunity, since there's no object identity, the VM has the opportunity to see, oh, this value type is the same one as that. If and when it has to be materialized in the heap, we can use the same object for all of them. I've seen memory dump analyses of a certain large commercial application server where the profile had, not only were there lots of strings, there were megabytes worth of strings of two forms. One was the string Y. The other was the string N. And there were megabytes worth of these things. Like, oh, duh, if it were a value type, then all of that could be optimized away. So I think we will look for opportunities to gradually evolve some things that would be a big win for everybody in that fashion. We've done so proactively with, for example, Java Util optional that was introduced in 8 as part of Lambdas, in support of Lambdas and streams. The specification for optional says, it strongly advises you do not depend upon object equality for instances of this class, because it may well become a value type in future.
Thanks for the talk. With the space of changes in API and the language, what is the recommended way to maintain code which you may need to run at older JREs, and yet you want to keep updating your code so that you leverage from the new one? So how to maintain code? In particular, you mean maintain a library that you want to work on 9 and later and use the newest features, but also still work on 6? Sort of. So there is a multi-release jar that's for binaries, but how do you manage the sources that go into that multi-release jar?
Right. So he alluded to this multi-release jar feature that we introduced in 9, which is specifically to help library maintainers distribute a single artifact that can work on an old release but use slightly different code on a newer release, yet still share as much of the code as possible. It's not the easiest feature in the world to use. I think with multi-release jars, we're still in the time frame of waiting for the IDs to catch up with it. How to do source layout, there are a number of different answers to that question. A lot of it depends on the build tool that you're using. So I think we're obviously answering questions and encouraging people to use them, but multi-release jars are the main tool there. So I think you already know it. I admit it's kind of clunky, but hopefully the tooling will improve over time.
Okay. You're done. Time's pretty much up.
Okay, thank you very much.